whoever can identify what video game this is from. I want the name of the game and the system. If you think you know, come on up. And the name of this talk is DCFluX and Moon Bouncer, and here's our agenda for this evening. And let me, it's great to be a winner, and aren't we all? So I'll start out a little bit about myself. Yes, I was a teenage engineer, started doing broadcast engineering in high school. Last year I did a talk called The Man with the Soldering Gun, but it was on Thursday. This is a picture of me living on the edge without a tower harness, and here's the obligatory picture of me sodomizing a cow. And if you look closely, you'll notice he is shackled and cannot escape. I come from a small town, Kingman, Arizona, which is 100 miles south of here, and by golly, when I walked past this, I had to take a picture of it because this is the stupidity we have here. Not only did he try to lock it to the light post that all you'd have to do is lift it up, he couldn't even fit the bike lock around his bike. So, yeah. So, the origins of this talk, I couldn't find a picture of this, so I had to use this. Recently, I was without internet for about 3 days. The reason was what we call in the broadcast industry backhoe fade. An illegal immigrant in one of Phoenix's many suburbs thought it would be a good idea to dig up a 150-foot section of 144-count fiber optic cable. Now get this, he was doing it because he wanted it for the copper. So I figured, hey, let's, when the internet fails, we pretty much want to come up with some clever way to communicate across the world, preferably without the aid of it. So let's start out with... So my talk will focus a lot if you're an amateur radio operator, and if you are not, why not? Hopefully this, I haven't gotten confirmation on it, but we will be giving amateur radio testing, hopefully. Usually we do that Sundays at 12 o'clock. And so here's my series of tubes that are useful for transmitting. We got the 2C39 on the left, which is good for about 100 watts. Next to us, the 3CX3000A7, which will do about 8,000 watts. Problem is, you need to build an amplifier to drive the thing. And on the right, there's a 4CX1000A, which will do 1,500 watts, no problem. But the biggest problem with coming up with these tubes is you can get a tube dirt cheap in the $20 range, but when I tried to buy a socket for the 4CX1000 here, it was like $2,000. So, if you don't need to change it, just solder wires to it and you're good. Other tubes that are useful for stuff is this here's a magnetron, which is useful for delivering power in the 2 gigahertz range. It was originally developed in World War II for use in radar systems. The last slide is a picture of it without the external magnets. I didn't get a picture of it while I was there, but the set of magnets here is in the Exploratorium in San Francisco, and the magnetron would sit in between there. And things have gotten much simpler since we started putting them in microwave ovens. Everything's a nice self-contained unit, so if you want to come up with a real easy way to get on 2.4 gigahertz with a lot of power, that's the way to do it. Also showing up because of a surplus in UHF television transmitters is klystron tubes. Ever since the digital television transition, analog transmitters are starting to show up on the surplus market. If you ask any chief engineer of a TV station, chances are he'll give it to you if you haul it out of there. These are some little klystrons that don't require the external magnets and cavities, but they only put power out in the 20 milliwatt range or so. Other tubes of interest are these guys, the traveling wave tubes. They're real good because one stage can do 40 to 50 dB of gain depending on the tube. So, you know, less than a milliwatt in will get you the full output power of the tube, usually in the 10 to 100 watt range. It's also very rare to find the traveling wave tube outside of its natural habitat, the traveling wave tube amplifier. So if you're in the market for one, definitely buy it in the amplifier form because it'll come with the power supply and it'll take all the guesswork out of it. Another interesting tube is the hydrogen maser, which is just like a laser, but with instead of the light is microwave. So it's microwave amplification, stimulation through whatever it is. Look it up. Pretty much the only tube that I have heard of that was this type existed here. The antenna structure that is on the right of the screen there at the Bell Telephone Laboratory Satellite Communications Center in Holmdel, New Jersey at about 1960. The steerable horn antenna sugar scoop used is for receiving to the right. This was in the 60s when they were playing around with passive reflectors, so they transmit with the antenna on the left and receive it back with the antenna on the right. So yeah, we're here to talk about moon bouncing, but not that kind of moon. But for whatever reason, I did find a moon bounce room. But no, we're here to talk about this one, Earth's moon. Pretty much about 3,400 kilometers in diameter, and it swings between two orbits, a perigee and an apogee, and so it has about 40,000 kilometers worth of swing between the 2 points, and it comes and goes about every 27 days and change. The original people that did moon bouncing was shortly after World War II. We did Project Diana, which the real idea behind Project Diana here was we were in the Cold War with Russia, and we wanted to know what Russian radar signals looked like. So the idea was that these signals were bouncing off the moon somehow, and we were going to be able to receive them. And so we did this test run with, you know, we basically took a surplus SCR-271 radar set, which was designed by Major Edwin Armstrong, the inventor of FM, by the way, and tried to bounce a signal off the moon. And here's a quick attenuation chart. There's some clever math that goes into it, but basically you can count on the moon to be between 5 and 7% efficient as a reflector. Plus you have to do the path both ways there. And these, I do have the perigee and the apogee, and you'll notice that there's about 2.1 dB gets added, or is that about right? Or it's about 2.2 dB added between perigee and apogee on a moon bounce. And you know, I just did some common bands here. The bands that are in bold and italic here, 2 meters, 70 centimeter, 23 centimeter, those are the ones most commonly used for future reference. So let's take a look at a quick path loss on Project Diana. So our radar set was able to deliver a 8,000 watt carrier, and we're about 256 dB on EME, and we actually on that radar set we actually had two antennas side by side, so we got the gain of the radar set up another 3 dB. Pretty much power double. Each time you double the amount of antennas, your gain goes up 3 dB, so if you're interested, that's why. But look at that estimated signal we've got there, negative 148. Who here's an amateur radio operator? Excellent. Anyone know off the top of their head what the sensitivity is of their receiver? Whereabouts? A gentleman said minus 120, and that's pretty good. But
that brings them to about there.
Gentlemen, that's not acceptable.
So how do we squeeze 28 dB out? Well, there are a number of ways we can do it. We can basically dip the receiver in liquid nitrogen or liquid hydrogen to make it colder. We can decrease the bandwidth, or we can try to decrease the noise figure by using better components. So here's a block diagram of what the Project Diana receiver looked like, and the big key is the receiver bandwidth is 57 hertz. And wow, if you're not careful with a bandwidth that small, the transmitter can easily wander out of the receiver where you're trying to receive. So I didn't want to do a formula, so I made a chart for you, and you can find this on your DEF CON CD, which you should have. So there's 3 columns here. 70 degrees room temperature. Negative 321 is the temperature of liquid nitrogen. Negative 457 is liquid helium. But you'll notice that you know, a room temperature receiver versus one dipped in liquid nitrogen, we get 16 dB more gain out of it. So, am I doing that right? Yeah, I didn't write these numbers down, so I'm just doing it off the top of my head. And you know, if we can come up with some liquid hydrogen, we get even better than that. Now, I'm sure you're wondering about 0 degrees Kelvin, and at 0 degrees Kelvin, theoretically, no noise is generated, and you have a perfect system. But to date, it has been impossible to make 0 degrees. And we've gotten really, really close, but I don't know if anyone's dipped a receiver in wherever the close to 0 is to see what the results are. But yeah, so let's run the numbers again with some stuff here. Negative 174, so we'll assume they ran it at room temperature. And here's the formula to figure out, you know, we can get a decibel rating out of the bandwidth. It's basically bandwidth log 10, and then you times that by 10. And we also have to add in the receiver noise figure. So basically, we got, amazingly, we got 1.3 dB to spare. And it was just enough to be detectable. So that was 1946. In 1948, someone said, great, let's bounce signals off the moon as a way to communicate from point A to point B. This comes from the notebook of James H. Trexler. Basically, he theorized that we could shoot a signal off the moon from LA to Washington, D.C., and as long as the moon is visible in both places, it'll work. And by golly, it did. This is a picture that was transmitted via facsimile, via the moon. That was, you know, he theorized that we could do it in 1948, and we didn't get around to doing it till 1960. And so we were able to bounce this signal off the moon. So the Navy was, the Navy did this. This is the picture of a USS Hancock, and it was transmitted between Honolulu, Hawaii, and Washington, D.C. And it was pretty brute force, the system the Navy used. It operated somewhere around 400 megahertz, but they had 48-foot dishes with 100,000 watt transmitters. So, yeah, the aliens must love us. First we're sending them pictures of Hitler, then we're sending them pictures of aircraft carriers. A little bit later here, in 1962, we went mobile here. This is a picture of the USS Liberty, which was an auxiliary communications relay, sort of like an early version of a spy ship. If you look towards the aft end of it, you'll see a 16-foot dish, and they had a 1,000-watt transmitter, which, you know, is enough because you got a 48-foot dish on the other end. So that could communicate as long as it saw the moon as well. But I forget which incident it was, but it basically got destroyed. There was a bunch of controversy about it because apparently, what was it? The Israelis attacked it, thinking it was some other country's spy ship, and then they're like, "Hey, we're American," and we're like, "Oh, okay, sorry." So here's some bandwidths of some popular modes that work for moon bouncing. The most notable one that gets used a lot is super slow CW, Morse code. And how slow is super slow? We're talking about 15 seconds for a DIT and 45 seconds for a DA. But because you're running so slow, a 100-watt transmitter looks like 1,000,000 watts. So you can look at that chart. Other modes on here are, I don't know if, I didn't have time to research this to see if anyone had done it, but PSK31 is on here because it's a really low bandwidth mode. And I suppose you could do it, but the thing is, the moon is moving, and you'd have to compensate for the Doppler shift. So you'd have to keep tracking the signal. If anyone's played with PSK31, it'll wander through the waterfall display, and you'd have to like keep clicking on it every 10 seconds or so. This JT65A here, that's a new mode, and I was actually surprised that it's wide bandwidth, because it's my understanding that that takes like 5 minutes to do a one-way QSO on it, but apparently it repeats itself a lot, and that's where it gets its robustness from. And I've heard of people doing sideband via moon bounce. Don't know if anyone's done it with FM yet, but here's the figures for, just the sake of this chart. So a bunch of you guys are nerds, and we're into Wi-Fi, and I figured, hey, let's see if we could make a 900 megahertz Wi-Fi moon bounce work, and I did it with off-the-shelf stuff. I got a 10-watt transmitter here because I was able to find one of those online, and that had a 12 dB preamp built in, and here's the path, and I figured use a 15-foot parabolic dish, and well, we didn't quite make it. Now, if somehow we were able to put a 15-foot dish with a repeater on the moon, it'd work just fine. So what about 2.4 gigahertz moon bounce? Well, this is with off-the-shelf equipment, but unfortunately I don't know anyone in Puerto Rico. But if we could build another Arecibo dish, you'd be able to communicate with 1 watt via moon bounce on 2.4 gig. So how about some giant freaking laser beams? So back during the Apollo missions, we put up these things on the moon. These are called, the thing on the left is called a retroreflector. Just like the reflector on a bike. The idea is that if a light beam hits it at any angle, it'll come back on the same path instead of going off at like 90 degrees like your traditional mirror would. So we've got these things on the moon, and well, there is enough beam dispersion on there that a beam about yay wide is about 7 kilometers in diameter by the time it gets to the moon, and about 20 kilometers in diameter when it returns. So if you really wanted to, you could talk across town by bouncing a laser off the moon. And here are the locations of the known retroreflectors that are up there. We've got here Apollo 11, Apollo 14, Apollo 15, and we have Luna 17 and 21, which were the landers for the little-known about Russian probes, the Lunokhod 1 and 2. Here's a picture of the Apollo 15 reflector. It's the one everyone used. About 3/4 of the ranges done on the moon use this reflector because it's the one that's the biggest. Now here's where it gets depressing. A 1 gigawatt pulsed laser beam delivers about 200 quadrillion photons in the pulse. We get about 3 or 4 back. Yeah, I said it'd work. I didn't say it worked good. So let's move on to practical methods. 2-meter moon bounce. This is kind of what we're into where I call moon bounce on the cheap phase. 1,500 watt amplifiers on 2 meters. You'd have to build one yourself, but might I suggest 16 110 watt VHF Master 2 PAs? configured with one driving 15. Because right now with the narrow banding of the commercial radio, these Master 2s are showing up free. So if you find the right guy that's got a bunch of them, he'll give you a truckload for nothing, the cost of gas getting out there to get it. But they're FM PAs, so they're only good for FM and CW modes. You probably can't run sideband or PSK through them. So basically we got our 1500 watts, and this 17-element Yagi here, Cushcraft makes, and I'm just using one because you're probably better off making an antenna on your own, because they want $350 for theirs, and they recommend that you run 2 or 4. So yeah, and but pretty much as long as we're running super slow CW or a mode that's narrow bandwidth, it'll work fine. Extra credit if you feed the signal from your radio into a sound card and use digital signal processing, it'll work even better. And the number of antennas you run really depends on how bad you want to piss off your neighbors. This is the 48 Yagi array of W5UN. I couldn't get an exact number on the gain, but I'm going to estimate about 36 to 40 dB gain. This thing is so bad, so big. To rotate it, he's got a pivot point on the center, and the radius is on a railroad track. And moving right along, 2.4 gig moon bouncing. And yeah, I know someone's going to say, hey, that's an inverter microwave, and I'm sorry about that. This was the picture I found, and I didn't find another picture, but you want the old school microwave, because this is what's in there. Real simple to understand. Basically, we've got one transformer feeding a cap and a diode. So on the plate of the magnetron, we've got about negative 4,000 volts, and we've got about 3 volts for the filaments. But if you get the inverter, I couldn't find a schematic of an inverter one, and the parents wouldn't let me tear theirs apart, so I don't know what's in one. But you can mod it. Pretty much the magnetrons, the problem with a magnetron running on its own is the frequency changes as it heats up. So the idea is if we vary the current going into the plate and we phase lock loop what's varying the current, we can lock it to a frequency. So then it becomes useful for moon bounce because it's always on a known frequency at any given time. You can still use it, but someone, you'll drift on the other end and make the other guy mad because, he'll copy your DIT, and then when you go to transmit a DA, it'll heat up and go outside the receiver bandwidth. So that's why we want a phase lock signal for that. Or if somehow you can come up with a circulator that will handle 1,000 watts, we can do injection locking. So about 2% of the output power, if we come up with another 2.4 gigahertz transmitter that's, say, 10 watts, and transmit into the third port on the circulator, that'll go into the magnetron and lock it, and we get more power out. So we can basically use a magnetron as an amplifier. So here is the path attenuation data on that scenario. Basically, I'm about a 1,250 watt microwave oven will get you about 800 watts of RF, I figure, because they rate them by the voltage or the wattage, the AC input, not the actual RF power. So if you come up with a 12-foot dish and basically duct tape a microwave oven where the LNB goes, it should work. So where does one find surplus parabolic dishes? Well, by golly, look around. If you see one on a mountaintop that's pointing into the ground, chances are you could have it. If you see one blown into the wind, chances are it's good. Now this one's in use. This is actually called a simulsat, but the guy had one sitting in the crate because the The original one they sent him, the place where the LNB goes, the feed point, was damaged. So instead of sending him a new feed assembly, they sent him a whole new dish. So he's got the reflector sitting there, and if you ask him nice, he'll get it. Who knows where these dishes are? Anybody? What? Someone said here? Yep, they're here. They're on top of caddies. And I don't know if they're in use or not, but, you know, find a guy and ask. I'm very proud of this picture. I drove past this. If you come across a dish that is pointing into the horizon east or west, chances are you can have it. Also, if you look behind the dish, you will see two cable reels of stolen 750 series hardline from the local cable company. I'm not really sure what they were doing with that, but yeah, the gentleman noticed me taking these pictures and kind of came out in a wife beater with a coffee and mustard stain and said, "Hey, what are you doing?" I'm like, I was inquiring if this dish was for sale. It's like, by golly, it is. So if you ask nice and you haul it away for them and give them a 30-pack of Keystone, it could be yours. So how wide do you need your antenna beam width to be? Well, there's some clever math that went into it, but I'm not about formulas, I'm about results. So basically, approximately half a degree wide. Otherwise, you're sending pictures of Hitler into space. So what if your dish has holes in it? By golly, I calculated that out for you too. Pretty much most of the C-band dishes have 1/4-inch holes on them, so they're good for, you know, the C-band range up to 4.72 gigahertz. So they'll run just fine on 2 gig. But if you're going to be doing stuff in the KU and K range, you probably want to go with a solid dish. And fiberglass dishes are not solid. They actually have mesh inside. They've just got fiberglass encased around them, so you might have to take a chunk out of one of the edges to see how thick the mesh is. So now we will get to artificial satellites. Everyone knows about this one, launched in October 1957. By golly, it's Sputnik 1. It beeped on 20 and 40 megahertz until the batteries died, and a lot of people didn't think it had any smarts to it, but the length of beeps that it transmitted were actually the temperature inside and outside the satellite, so we got some useful data out of it. And then Russia sort of got into hot water by launching a dog on Sputnik 2. This is Laika, the barker in Russian. It was controversial because Laika was launched with no intention on being returned. The idea was you see that thing in front of her, that was an automatic dog feeder, and apparently on the 5th day there was like a poison cartridge, but unfortunately Laika didn't survive that long. So then later on we launched, or the Russians, they had 2 dogs and a camera. And this is noteworthy because this picture, the CIA was able to take a signal from a slow scan television camera that the Russians had that they had never before seen and decode it and get a useful picture out of it. So where were we doing? You know, we've got some artificial satellites, but I'm gonna talk about this one because we're about moon bouncing. This here is Echo 1A because Echo 1 exploded on the launch pad. It is a aluminum-coated mylar sphere that's about 100 foot in diameter, and the idea was we could still use all of our moon bounce infrastructure, but you know, obviously if the moon's not in your field of vision, you can't use it. So we basically made an artificial moon for bouncing the signals off of, and yeah, it was only recently revealed that that was one of the uses. The other uses were we were still looking for Russian radar signals bounced off of it, and the CIA used optical telescopes to aim at this thing so they could gather targeting information on cities in the Soviet Union. And later on they launched Echo 2, which was basically the same thing, but it was a slightly larger diameter, 135 feet instead of 100, and it had a much smoother surface so the telescopes would work better. This is what I consider the first real communications satellite. This is SYNCOM 3, and I consider it the first real satellite because it's the first geostationary satellite. Now that means that it is at an orbit and a speed to where, when observed from the ground, it does not move. So that means you no longer had to track it with satellites. It used 2-watt traveling wave tubes, and it was able to broadcast the 1964 Olympic Games live from Tokyo to the U.S. The 5 megahertz wide channel was enough for one full duplex telephone call, or 16 one-way teletype circuits, and the 13 megahertz wide channel was good enough for black and white TV. And, well, now we've got a few satellites up there. There's an estimated 1,500 satellites in geostationary orbit, plus however many we've got going in polar, and I won't tell you what we consider space junk, because that's just depressing. So here's a satellite you can actually use if you're a licensed amateur radio operator. This is AMSAT Oscar 51. I believe the call sign here is Echo. But it depends on the amateur satellite. These will be in your field of view for 10 to 15, maybe even 20 minutes, some of them. What do you need to use it? Well, I got in my hand a Kenwood THF6 dual band transceiver. Other good radios would be like the Yaesu VX7, VX8 series. You want one that has true dual band capability, not band at a time, so actually 2 bands running on the radio at the same time. You can still do it with like a FT60, but then you have to change the channel back and forth, and that might get annoying. And one of these guys. This here is the Arrow 2 antenna. We have 3 elements worth on 2 meters and 7 elements worth on 70 centimeters. So if you know the time and the rough place when the satellite is going to be overhead, you can just go outside and go like this and kind of look like a dork to your friends, but joke's on them because you're talking through a satellite. This antenna, and I also have the diplexer in here, which is fairly expensive. I discovered Thursday when I went to the local nerd store. Sets you back about $140. Or, if you're real hardcore, you can just build everything on your own. So how about other satellites that are not amateur related? This here is Telstar 28, also known as Sierra 2205. It's a new hybrid satellite because it has basically all 3 commercial satellite bands. These are the number of transponders. We got 22 on C-band, 36 on KU, 24 on KA, and it uses bent pipe technology. And I actually got that term from the brochure, so I think it kind of works like this. So really what's on there is what's called a linear transponder, and this is an oversimplified block diagram. Basically, we have an input antenna that's going into an amplifier that is being mixed with a local oscillator and then amplified again with a traveling wave tube, and we have an automatic gain control circuit so that the power out of the traveling wave tube does not exceed whatever its limit is, usually 10 watts, and then we go back into an antenna. Other satellites, I should have put this slide a little later, but here is the coverage of one of these satellites. Pretty much covers the entire continental United States and all of Hawaii with a decent dish. It'll cover up into Canada, but The further north you get, the higher gain antenna you have to run. And here's a clever chart. I just did it average. So we have all the frequencies that the commercial satellites use, and I just averaged it here. So this is one-way path because we're not bouncing anything off of stuff. So let me introduce you to my friend. This is my friend Hugh. Hugh is from Kingman as well. I found him on the roof of a rental building that a friend of mine recently acquired, and he called me. He's like, "Hey, got this thing on the roof. You want it?" I'm like, "Yeah." So this is basically what is inside Hugh. Hugh is the outdoor unit from a HughesNet HN9000 bidirectional satellite system, a VSAT, which is very small aperture terminal. This is what's in here. I apologize to the folks at home, but I have to use a laser on this because I'm running presenter view. Basically, this gold part in the center here is the business of the transmitter. We have this is a PLL and the lock circuitry here, and we go into a frequency doubling mimic and then a 1 watt output mimic, and this is the actual antenna output port. Now the rest of this, you got your switch mode power supply here, and this is some custom BS HughesNet part that I don't know what it does. Probably controls whether the thing is in transmit or receive mode. So basically what I did to hack this guy is I shorted out this transistor, these transistors, there's some transistors here, and basically jammed the thing in the center on. Here is a block diagram here. I was all excited, but unfortunately, as I knew it was wrong, but I hacked it anyways. So I found out that it is a Ka band satellite, and it would be much more usable for me if it was the Ku band, and I will tell you why a little bit later. But basically what's going on here is the indoor unit, which I don't have, delivers a signal between 229 and 241 megahertz, and the PLL that's inside here basically has a fixed divide by 64. Hopefully my demo will work. You all see that red LED there? Yeah, that's my unlock indicator, which I brought out because, by golly, when I found the data sheet on the PLL, everything was there right off whoever designed this used the schematic right off the data sheet, so double thumbs. So basically, it's a giant, it takes an input signal and multiplies it by 128. So a 220 amateur band signal comes out somewhere in the 29 gigahertz range. So while I was playing with it, I didn't bring my HP 8924C because that weighs a ton and a quarter. But just for kicks and giggles, I have here a DC power inserter, and I just put an antenna on it off of a 220 handheld. So when I key up, oh, someone by the door that way, listen and see if someone screams. But I am keying up on 224.9, and that is enough with just me keying it here to make the thing lock. So theoretically, we're putting out a beam on a beam on 30 gigahertz somewhere that's 22,000 watts ERP. And this is a part 15 device. So probably somewhere up that way. Maybe. I don't know. I don't want to stare into this thing while it's transmitting. I probably should do this. That's right. No one gets sued. So this is why it's depressing. It talks to this satellite here, also Spaceway 3, Sierra 2663, and no one really knows what goes on inside this thing. Some stuff claims that it's bent pipe technology. Other stuff says that it's got a demod, remod on it and actually makes the internet work inside of it. And this is the sad part. I apologize for the picture. It was the best I could find. These use spot beam technology. So this is a spot beam reflector. And each one of these facets was CNC milled. So what's going on here is there's like 12 apertures on the side of the spacecraft. And
it's a series of tubes.
So the input tubes bounce off the main reflector, off of the spot beam reflector, and then into their associated LNB on the spacecraft. And the problem is, I don't know where our input tube, we are in input tube 33 right now, I don't know where it comes out at. Also, there are two different sets of frequencies here, a VSAT set and a gateway set. So like I said, if it was the KU, I was hoping for you guys, if it was the KU one, that I would be able to send a signal through the satellite and have you listen to it, but unfortunately I got it on the bench and I was like, no! But hey, these things happen. So how about when satellites disappear unexpectedly? There are several natural causes that'll do this. Meteorites, solar flares, leaking capacitors, exploding batteries, tin whiskers, you name it. There's been a number of satellites in recent history that have disappeared without a trace. Galaxy 4 comes to mind. I believe the last one that went rogue was Intelsat America's 13, but I might be wrong on that. And no, sometimes this happens.
Wow, excellent.
So, government agencies recently have developed clever ways to shoot down satellites of people they don't like. China has modified ballistic missiles. The United States was successful shooting down a satellite with a modified standard surface-to-air missile off of a Navy ship, and lately we've been playing around with more of those freaking laser beams. Now the Russians are hardcore. The Russians had a 23 millimeter gun on the secret Russian spy lab, the Almaz station, and lately, they saw China and the U.S. playing with missiles, so they're like, oh yeah, watch this. We'll just send we'll send an old weather satellite into one. That'll teach you. How about taking down my bad. How about taking down a satellite from your backyard? Now, I won't tell you what satellite these frequencies are for, but yeah, the key resource for learning about this stuff is the FCC's International Bureau, not the regular one. So this satellite I'm looking at here has two sets of frequencies, and the 20 and 29 gigahertz ones are spot beamed. So just so you know that, you have to figure out which spot beam it comes out at. And when the spot beams don't work, the lower set is used for when the thing is changing orbit or in emergencies. But theoretically, both sets are on all the time. And the big problem here is trying to figure out, I have the emission designator, and I know the frequency it goes in on, but I don't know what the codes are, and this is where you have to social engineer someone that works at the place that built the thing. Although it is theoretically possible just to jam both sets of frequencies, so the thing no longer gets station keeping information and then 2 or 3 months wanders so far out of orbit that no one wants to use it again. And well, if you could come up with what codes the thing actually spoke, you could send it into parking orbit, which makes it worthless, or enter it into the atmosphere, or just shoot it, just command the rockets to turn on until the thing runs out of fuel. But don't tell anyone I told you to do that. You could get banned. So I apologize I didn't have time to build one, because unfortunately I was recently the victim of a premeditated breakup. But I'm waiting on some better technology to do this, and other people have done it. But there's actually a company now that I believe for $9,000 will launch a weather balloon that you can use as a satellite. And, you know, I got this idea. This is a bad picture for it, but most of the time the jet stream hovers right over where I come from, Kingman and Las Vegas. So you just figure out when the jet stream's overhead and shoot it into there. So, you know, this is actually a fairly cheap system I came up with. You use your WRT-54GL. You know, everything's off the shelf. Now, I put on here a latex balloon. If you could find a mylar balloon, you'd be much better off, because the helium leaks a lot less through it. And I was going to build an altitude station keeping system with a airsoft gun. Just fill it with helium. So here's what you know, our weather balloon would get us at 2 meters, and basically this is just so I can show you that, yeah, we're over Vegas and Kingman. Here's what our coverage looks like at 60,000 feet. Now this is just with, you know, your standard 24 dBi grid dish antenna on the receive end and the 9 dB one on the weather balloon, and we get a little more coverage at I'll toggle them back and forth. We get a little more coverage between 80,000 and 60,000 feet, but nothing to write home about. So it looks like we're getting ready to wrap up. So real quick, here's some other stuff you can blame me for. Basically, if you take a linear transponder like we had on the satellite, and for the local oscillator, use the offset of your favorite repeater, whether it's on 2 meters or UHF, and just get it really close, and you can really make whoever owns that repeater's life miserable. And also, if you modify the microwave oven transmitter I showed you, just put a sawtooth generator in place of the PLL circuit, and by golly, you're jamming on 2.4. So if there's any questions, I will be in the Track 4 Q&A room in a quick, assuming it didn't get inadvertently locked, and if it did lock, if anyone's got lock-picking skills, meet me over there. And hopefully if the people with DEF CON liked my talk, I will see you sometime next year in License to Transmit. And thank you for attending, and try to enjoy yourselves the rest of the day. For whoever can identify what video game this is from. I want the name of the game and the system. If you think you know, come on up. And the name of this talk is DCFluX and Moon Bouncer, and here's our agenda for this evening. And let me, it's great to be a winner, and aren't we all? So I'll start out a little bit about myself. Yes, I was a teenage engineer, started doing broadcast engineering in high school. The tube dirt cheap in the $20 range, but when I tried to buy a socket for the 4CX1000 here, it was like $2,000. So, you know, if you don't need to change it, just solder wires to it and you're good. Other tubes that are useful for stuff is this here's a magnetron, which is useful for delivering power in the 2 gigahertz range. It was originally developed in World War II for use in radar systems. The last slide is a picture of it without the external magnets. I didn't get a picture of it while I was there, but the set of magnets here is in the Exploratorium in San Francisco, and the magnetron would sit in between there. And things have gotten much simpler since we started putting them in microwave ovens. Everything's a nice self-contained unit, so if you want to come up with a real easy way to get on 2.4 gigahertz with a lot of power, that's the way to do it. Also showing up because of a surplus in UHF television transmitters is klystron tubes. Ever since the digital television transition school. Last year I did a talk called The Man with the Soldering Gun, but it was on Thursday. This is a picture of me living on the edge without a tower harness, and here's the obligatory picture of me sodomizing a cow. And if you look closely, you'll notice he is shackled and cannot escape. I come from a small town, Kingman, Arizona, which is 100 miles south of here, and by golly, when I walked past this, I had to take a picture of it because this is the stupidity we have here. Not only did he try to lock it to the light post that all you'd have to do is lift it up, he couldn't even fit the bike lock around his bike. So, yeah. So, the origins of this talk, I couldn't find a picture of this, so I had to use this. Recently, I was without internet for about 3 days. The reason was what we call in the broadcast industry backhoe fade. An illegal immigrant in one of Phoenix's many suburbs thought it would be a good idea to dig up a 150-foot section of 144-count fiber optic cable. Now get this. He was doing it because he wanted it for the copper. So I figured, hey, let's, when the internet fails, we pretty much want to come up with some clever way to communicate across the world, preferably, without the aid of it. So let's start out with... So... my talk will focus a lot if you're an amateur radio operator, and if you are not, why not? Hopefully this, I haven't gotten confirmation on it, but we will be giving amateur radio testing, hopefully. Usually we do that Sundays at 12 o'clock. And so here's my series of tubes that are useful for transmitting. We got the 2C39 on the left, which is good for about 100 watts. Next to us, the 3CX3000A7, which will do about 8,000 watts. Problem is, you need to build an amplifier to drive the thing. And on the right, there's a 4CX1000A, which will do 1,500 watts, no problem. But the biggest problem with coming up with these tubes is you can get an analog transmitters are starting to show up on the surplus market. If you ask any chief engineer of a TV station, chances are he'll give it to you if you haul it out of there. These are some little klystrons that don't require the external magnets and cavities, but they only put power out in the 20 milliwatt range or so. Other tubes of interest are these guys, the traveling wave tubes. They're real good because one stage can do 40 to 50 dB of gain depending on the tube. So, less than a milliwatt in will get you the full output power of the tube, usually in the 10 to 100 watt range. It's also very rare to find the traveling wave tube outside of its natural habitat, the traveling wave tube amplifier. So if you're in the market for one, definitely buy it in the amplifier form because it'll come with the power supply and it'll take all the guesswork out of it. Another interesting tube is the hydrogen maser, which is just like a laser, but with instead of the light is microwave. So it's microwave amplification.